Imagine this. You are working on a back-end application that needs to send thousands of emails, process large files, or generate some reports. If your server tries to do all of that work immediately, best believe your application is actually going to slow down and your users are going to face some delays. And of course, you are going to overwhelm your resources. And this is a very common problem in modern applications when you have long-running tasks or CPU-intensive tasks that need to run. So how do you actually fix that? Well, there's something called message queues, and it basically consists of you taking those tasks, adding them to a queue, and then you would have some consumers or workers consume those tasks and then run them in the background without actually affecting your resources. In this video, we are going to use something called BullMQ with NestJS to fix this problem, so let's get started. To better understand how BullMQ comes into play and the message queuing and all of that, let's take a basic example where our backend server does everything immediately and it's a bit messy. So let's say we have some clients and they can make some requests such as placing an order or uploading a video. Our backend server will have to perform some immediate tasks such as validating the order, maybe the address and all of that, the payment method and so on. And then we should also update our inventory in the database. Maybe we should save some video metadata for the upload video process and so on. And our backend server will also have to do some heavy tasks such as compressing the video, generating a report for the order payment, the receipt, sending an email with the details and so on. Well, all of that is going to overload our system and it's going to be tiring. And here is where BullMQ comes into play. With BullMQ, we can actually schedule those heavy tasks, when they should be processed, how they should be processed, and so on. And as you can see, we have also a queue, which in the case of BullMQ is hosted on Redis. So basically BullMQ uses Redis as its backend. And if you take a look here, we are still placing an order, uploading a video. Those are requests from the client. But this time, our backend server is just going to handle the immediate tasks, such as validating the order, updating the inventory, and so on. And then it's going to delegate the heavy tasks to BullMQ or to that queue on Redis. So basically compressing videos, sending email, generating reports, all those tasks are going to be delegated or stored on that queue and will be actually waiting until being processed or consumed by one of those BullMQ workers. Now, depending on our configuration, it can behave in different ways. So for example, we could say that this first worker can, for example, run 5 jobs concurrently, while the other one can only run 2 jobs concurrently, for example. We could introduce some priority for the tasks depending on the job importance and so on. We could also implement some retry mechanism where if a job fails, for example, let's say sending an email or generating a report, it would actually stay in the queue and attempt to be processed again. We can configure a lot of things. Now, before moving on, I want to point out one more thing because I don't want you to have any misconception at all. Now, if you take a look at this diagram again, we can see that we have a backend server, which could be a separate application. And then we have the BullMQ workers, which could be, each of them would be a separate application as well, but it doesn't have to be the case. So it could be on the same server or the same application. Of course, in that case, they would be using the same shared resources. So you might actually have the BullMQ worker inside of your backend server, okay? Infrastructure-wise, this costs less. And maybe if you're starting out or you're not really scaling yet, it's fine if you have those BullMQ workers or consumers inside of your backend server all together, sharing the same resources. Now, you might be asking me, isn't that defeating the purpose? Well, at first, it's fine if you start that way. You can still benefit a lot with BullMQ since you are still using that queue to actually schedule those jobs. You still have that retrial mechanism that I just talked about, and you can still prioritize some jobs over some jobs, and you can still specify the concurrency number, and you can still add some throttling or rate limiting. That way, you always ensure that only a certain amount of jobs is running at a given time. So you are still actually managing your resources in an efficient manner while using BullMQ. So let's get into coding. The first step is pretty simple. In our NestJS application, we first need to install the BullMQ package. Then we would need to register the Bull module and specify our Redis server credentials. Then we would need to register a Bull queue. Just like we saw previously, we would have a queue that we would send jobs to. And of course, we can have multiple queues. based on what we need, based on our system architecture. And then finally, we will be able to send jobs to the queue. This is from the producer side before actually consuming those jobs. So let's get started. The first step, we would need to install the two packages, NestJS/BullMQ, which is the wrapper that NestJS created, and then the main BullMQ package. So let's do that. With that done, we can now register this bull module by using for root as usual. And then here we have some configurations that we can send. The first one is connection. And here we can specify the host for our Redis server and then the port. Now, to run Redis locally on my machine, I went ahead and opened up my Docker desktop and then pulled the Redis image, which is officially from Redis. And then you would press and run. And here for the host port, I just set this default port. And then I ran that container, which is now here, as you can see. Now, to be able to visualize that data, of course, we can use some Redis commands. So let's open the Redis CLI, check it's working, ping pong, and then we could say keys, and then we can see that we don't have any keys. Nothing is stored on our Redis server yet. But to better visualize that, I like to use a tool called Redis Insight. So you can download this for free, just like you have MongoDB Compass for Mongo, which is a visualizer, which is a pretty good tool. This is the same here. So it's pretty easy to use. So all you have to do is just add a Redis database, and then here you can add your connection. So I already have a local connection. I'm gonna open it. And as you can see, we don't have any keys yet, but this is going to change in a bit. So I specified localhost as the host, and then this is the default port that Redis is using. And then if we take a look at other configurations, we have some default job options. So if you take a look here, you can see that we have attempts. If you remember, I previously mentioned that we can have some retries for our jobs. So let's set this for a default of 3, for example. So if a job fails, we can keep trying to run it up to 3 times. And then we can see that we have some delay, the amount of milliseconds that a job needs to wait at least inside the queue before being processed by a consumer. We can specify LIFO, so last in, first out. By default, it's FIFO, so first in, first out. We can specify the priority of the jobs, remove on complete or remove on fail. So we can specify if we want to actually remove the job data from Redis once it's completed or failed. So we could set that to true or false, and we can also specify a number, how many jobs we want to keep stored, and so on. Now I move to step number 3, which is registering a bull queue. So you can easily say bull module.register queue, and then we can give it a name. Now, if this queue doesn't exist, it would create it. If this queue already exists, it is going to use the existing queue. Now, of course, you can have more queues. So you could just add a comma, and then here name, and then you could have one for emails, for example. So each queue would have jobs of a certain types, or you can use the same queue. Like, it all depends on your architecture here. So let's go ahead and just use one queue for this example, which is going to be called video. Now, if we open this Redis Insight, we can see that we now have one key inside of our Redis, and the key is bull. So this is by default from bull. Then we have a semicolon, which is a convention in Redis when you have different parts of the key name. And then we have video, which is the queue name that we specified ourselves when registering this queue. And then finally, this meta part. And this is by default as soon as I ran my server. And this just shows us the version of BullMQ and some other options. Now let's see how we can actually add jobs onto that queue that we just created. I turned this app controller into a video controller with this prefix. This could be anything, of course. And then I added this route handler of process, which is going to process the video. For now, I'm just returning a response with this message, but let's see how we can actually add jobs to the queue. So here we can use a decorator called inject queue, which is from NestJS BullMQ. And by the way, of course, everything here, which is actually bull module, is from NestJS/BullMQ as well. So here we can use inject queue, and then here we can specify the queue name that we want to inject, which is the same queue that we have created here, which is video. Of course, you can add this to a constant so that you don't have to type it everywhere, every time. But to be quick, I'm just gonna add it like that. And then we can just call this, let's say, video queue, which is going to be of type queue from the main BullMQ package. With this in place, we can now use this video queue. So let's say this.videoqueue dot, and we can see that we have some methods such as add, which is the most commonly used method, which just adds a new job to the queue. We can see we have add bulk, so in case we want to add an array of jobs to the queue, we can do that. We have clean to clean the queue, close, and so on. In this video, we're going to focus on add. If you open this up, we can see that we can actually give a name to the job. Now, I'm just going to call it process, let's say. And then here we can pass in some data, which is the data of the job that needs to be processed. Now here, let's assume that we have maybe a file name. Of course, this here wouldn't be hard-coded. It could be from a body here and so on, depending on your system. But just for the case of this example, let's just say best video is the file name, file type, MP4, and we could have any other piece of data that we need here. So this is basically what is going to be added to our video queue anytime we actually call this process video endpoint. Now, if you take a look at add, we can see that it returns a promise. So we could actually just await this. And now let's see what happens when we call this endpoint. So in Postman, let's open this route, video/process, and hit send. As you can see, we got video processing job added to a queue. Let's open our Redis Insight, refresh, and as you can see, we actually got many new keys now. We can see here that we have one which is showing the different events that are happening. So here we have this waiting event, then we have this added event, and the job name here is process. The job ID is 1. Now for the job ID, we can specify the job ID manually here. So if you take a look at add, it actually takes a name, the one we specified as process. It takes the data payload, which we sent here. And finally, it can also optionally take some job options. If you take a look at the job options, we can see the attempts, which is the same option that we specified here on the default job options for this Bull module. So we can override it here for this specific job if you wanted to. So attempts, backoff. Backoff is basically how long you should wait before each retry. So here, for example, you could say you need to wait 2000 milliseconds, meaning 2 seconds before each retry. You can also pass in an object and then specify the type of the delay, which could be exponential or fixed, and then of course the delay. So you can actually do a lot here. One of the other options you could specify is the priority. 0 is the highest priority, and then you can specify any integer you want. And as well, we can specify LIFO and so on. There are a lot of other options that you can specify. So let's go back to our Redis Insight here. As you can see, we have a lot of different keys now. This key is pretty important. It shows us the key name is Bull Video 1. 1 specifies the job ID for the job that just got created. If you take a look here at the data or the value, actually, we can see that we have a name field, which is process, which is the name that we specified for this specific job. And we have the data payload, which is the one that we sent with file name and file type. And we have some options. Here, we have this attempt 3 options. And this is because we specified in our app module this to be our default attempts number. And we have the timestamp, as you can see here. And we don't have any delay, and the priority is 0 by default. This is the highest priority. We can also see that on Redis, we now have another key, which is the wait list. So we can see here all the jobs that are still waiting to be processed. So this job hasn't been processed yet. And that makes sense. We haven't really created a consumer or a worker to process this job yet. So here we can just see that we have a job with ID 1, which is in the waiting list, waiting to be processed. Let's go ahead and add 2 more jobs. So I'm going to send a request, send a third request. And then here, if we refresh, okay, we can see that we have Bull Video 3. This is the third job. And then we have Bull Video 2 as well. This is the second job with all its data here, name, actual data payload, options, and so on. And if you take a look at the Bull Video Wait list, we can see that we have 3 jobs in the waiting state. And this is the first state that a job goes into before actually being processed and so on. Now let's go ahead and create our first worker, which is going to process the jobs from this video queue, because now they're all waiting. So it's pretty easy to create a processor or a worker, meaning the consumer that is going to consume those jobs from the queue. All you have to do is just use this processor decorator, which is from NestJS BullMQ, and then it takes an argument, which is the queue name. In our case, it's video, because this is the queue that we have registered here and created here. And then we would need to create a class. I called it video processor, you can call it anything you want, but you need to make sure that you extend this worker host class, which is from NestJS BullMQ. If you take a look here, you can see that we have this process method that actually gives us the job. So here, this is going to be our process method, and here is where we are going to retrieve those jobs and then process them. Let's stop this server for a second and now add a log here. So I'm gonna say got a new job, and then maybe let's show the job ID, job.id. And if you take a look at job, you can see that we have data, which is the actual payload that we sent here. We can have the job ID, we can see the job progress, which we're going to talk about in a second, and so on. Let's go ahead and run our server again. And this time, don't forget, we have 3 jobs that are waiting in the queue to be processed. So let's see why they're not being processed. Well, simply, there's one more step that we should do after creating our worker, which is taking this video processor or this worker class that we created, and we need to inject it in the providers array where it should be used. Now, of course, I'm adding everything in app module because it's a small app, but if you have a huge app, you would add them in their specific modules. You don't have to add them in app module. So let's go ahead and inject this as a provider and restart the app. And as you can see now, we have actually consumed those tasks. Even though those API calls were made a long time ago, we didn't keep our clients waiting, okay? We have processed those jobs as soon as we were able to. And now if you go back to Redis Insight and refresh inside of this waiting list, as you can see, key name doesn't exist. We no longer have this waiting queue anymore. And if you take a look at, let's say, Bull Video 3, which is the 3rd job here, we can see that it was processed because we have this processed on key, and this is the timestamp. And then it shows the return value. Now we're not returning anything in our code inside of the worker here. We don't have a return statement. So this just shows null, and we have this finished on key, which shows us that this job has been completed. And when a job is completed, it either goes to completed or to failed. So this is the new state. In our case, it was completed successfully. It didn't throw an error, it didn't fail. So we can see that it's inside this Bull video completed sorted set. If we take a look here, we can see that we have 3 jobs, which is member 1, member 2, and member 3. Those are the job IDs for the jobs that were actually completed. Now, if you remember, we said we have some configurations here. So inside of default job options, we can actually specify remove on complete. You could set that to true. In that case, it would remove the completed jobs once they are completed, so we don't have some more memory being used here. Now, I'd say a good practice is maybe to keep the last, let's say 1000 jobs, okay? And for failed jobs, we might maybe keep the last 3000 jobs, depending on your use cases, the importance of debugging, and so on. So I'll just keep that for now. Now, to make this realistic, I added some delay, so each job is going to take 5 seconds to complete the processing phase, and I just added a log, got a new job with this ID, and then job with ID whatever completed. Let's open Postman and hit send. As you can see, we got a new job with ID 4, and then it's going to take 5 seconds until we get this job with ID 4 completed. Now, what happens if you actually send multiple jobs at the same time? So I'm gonna hit send 3 times now. 1, 2, 3. If you take a look here, we only got 1 job now, job 5, and then it completed before actually going to job 6. And then now, after it completed, it went to job 7. But if you remember, I said that we can actually set the concurrency number for each worker. So I said we can specify how many jobs can run concurrently. So here, if we take a look at processor, we can actually send some options here. So one of the options is concurrency. If we set this to 3, it would mean that it can process 3 jobs at a time from the queue. So let's come here and hit send 3 times, 1, 2, 3. And if you take a look, we got 3 jobs working together, and then they got completed. Each job didn't have to wait until the previous one to complete before being processed. So this is the role of concurrency. Of course, if I were to send more than 3 jobs, so let's say 1, 2, 3, 4, 5, 6, we only got 3 jobs at a time. And once each job got completed, a second job in the waiting queue can now be processed, as you can see here. So this is pretty nice. Now, it's not really clean to add logs when we get a new job and then when it's completed inside of our process method. BullMQ actually gives us some event listeners that we can listen to. So let's see what events we can listen to. I added 2 event listeners. OnWorker event is the decorator that you use to register a listener. And here we have a list of options such as active, closed, completed, and so on. If we add active, this is when a job is actually now active. It started being processed. And then completed, once a job is completed, of course, we can add one for failed as well. So let's go ahead and let's say add one for failed. Let's call it on failed. And in the parameters, we have access to this job object. So we can check the job ID, the job data, the job number of attempts, the job progress, and so on. We're going to cover those properties in a bit. But for now, let's go ahead and move this got a new job inside of onAdded, and let's move job completed inside of completed. And let's test our code just to make sure that those listeners are working right. I'm going to open Postman, hit send 1, 2, 3 times. And as you can see, we got a new job with ID 17, which is now not inside of process, but inside of the proper event listener for the active state of that job. And then same thing for completed. And here, this should be failed actually. Now, if you take a look at our Redis database here, we can see that we have many jobs that were completed. If you take a look at the completed set, we can see all those job IDs, everything here is completed. We don't have any job failed. We have a lot of events here, as you can see in this key, bull video events. Now, let's try to fail some jobs and see how we can retry them with the retry mechanism. So let's make some modifications. First of all, inside of onFailed, I added a log, job ID failed, and then attempt number. And here in the job, we have this property, attempts made. So this is just the one I'm using. If you take a look here, it's the number of attempts after the job has failed. It starts with 0, okay? And then let's say here, after 3 seconds of processing, we get an error. So I'm just gonna throw an actual error. I'm gonna say, I don't know, file corrupted. This is the reason for this error. Let's run our server, and just to keep things clean, I'm gonna just delete all the hashes here. Let's refresh, and now this is pretty cleaner now. Okay, let's open Postman again, and this time send a job, video processing job added to the queue. And then, as you can see, we are getting some logs here. Got a new job with ID 20, job with ID 20 failed, attempt number 1, got a new job with ID 20, job with ID 20 failed, this was attempt number 2, and finally it failed again, and this was attempt 3. Now, if you open this Redis Insight view here and we refresh, as you can see, we have this bull video 20, which is the ID of the latest job. And if you take a look here, we get the finished on timestamp, okay? And of course, the name of the job is process, like we said before. And this time we can see that we have this failed reason key. And we can see that file corrupted. So this is the reason why this job has failed. And here we can see the stack trace as well. And this is of course because we manually made it fail by throwing this error here. And the reason is whatever message we provided inside this error constructor. And we also got this bull video failed set, just like we have this complete set. And inside of failed, we have this 20, which is the job ID for the failed job, which is this job right here. Now, of course, we can modify the way the retrial work. So for example, inside of app module, just like we have attempts, remove on fail, remove on complete, we can also have backoff. And inside of backoff, we said we could either add a number or the backoff options, which were exponential fix and then the delay. Now, by default, it's gonna be fixed. I'm just gonna say 2000 milliseconds, meaning 2 seconds. So now after every failure, okay, the job is going to wait at least 2 seconds before being processed again if our processors are currently taking any jobs, meaning if the concurrency number is met, it's not already running 3 jobs in parallel or whatever. So let's go ahead and hit send. Now let's take a look at the logs. Got a new job. After 3 seconds it failed, but this time it waited 2 seconds before attempting to run again. So as you can see, there's a delay of 2 seconds every time. Of course, you can play around with those options to fit your requirements as much as you want. I just want to show you them quickly. So if you go back to video worker, instead of using concurrency, you can also use something else, which is, what was it called, limiter, where you can specify that in a duration of, let's say, 10 seconds, so 10,000 milliseconds, the max number of jobs that could be running is 20. What this means is that we set a limit that this specific processor or this specific worker or consumer, because it's decorated with add processor, can process up to 20 jobs maximum in the span of 10 seconds. So here we can limit the number of jobs that can be run in a specific duration. Okay, so this is kind of similar to concurrency, but here we also have this duration variable at the same time. And this is a good approach if you want to make sure you're always controlling how much resources you're using, okay, at a time or during a duration. So you avoid actually overloading your CPU and crashing your app and so on. Now to show you how we can actually show the progress of a job, because inside of the job, we also have a property called progress, which we can also store here. And if you take a look at job, we have name, data, ID. We have a lot of things actually that can be useful. So let's focus on progress for now, which is on job.progress, which is going to show you a number or an object. Now in our case, we're going to assume that to process a video, there are 5 different steps. And for each step, once a step is done, we need to increase the progress percentage. So we have a for loop here, which starts from step 1 up to step 5. This is just to simulate the steps. And then for each step, we're going to wait 3 seconds until it completes. And then after that, the progress would be the step divided by the total steps times 100, of course. This way we get our percentage. And I just rounded it to get a round number. And we can use a method on the job object, which is update progress, okay? Which, if you take a look, it simply just updates a job progress and then saves it or stores it in Redis. And good thing, just like we have event listeners for active, completed, failed, we also have one for progress. So if you take a look here, set of active, we can add progress. Let's call this method on progress. Of course, you can call it anything you want. And here, let's just say job with ID, whatever. And then let's show the job progress. So percentage completed. So for example, job with ID 5, 50% completed, and so on. Let's save this and run our server again. And this time for each step is gonna wait 3 seconds, update the job progress. Once the job progress is updated, we're gonna listen to that event, and then we're gonna log the percentage of completion. So let's go ahead and send a new job. We got a response, client is not waiting, everything is good. We got job completed with 20%, 40%. Now if you open Redis and refresh, if you go to that job, which is ID 22, okay, if you take a look here, let's refresh. As you can see, it already finished. And then we can see the progress is 100%. So it has completed. And if you go to the completed set, if we scroll all the way down, we can see job 22 is present right there. Let's hit send again. Now it's gonna be job 23. If you take a look, if we refresh, progress is now 20%. If we refresh, now it's 40%. We refresh, it's 60%. So this is pretty beneficial, I would say. Now, in case you had maybe an antivirus running some scans, you wanted to show the end user the percentage of completion of that scan. Inside of onWorker event of progress, you could actually here maybe have this .websocket_client.emit, and then you would specify maybe progress and then the actual progress percentage. So you can do a lot with BullMQ. You can do a lot of things. You have a lot of configurations. This is a really powerful tool to actually run background tasks, heavy tasks. You can literally configure the retrial, the concurrency, the limit of the tasks being ran, and so on. Just like we have worker events, like here for example, when this worker is processing a job has been completed by this worker, we can see all of those events. We can also have queue events, which is kind of considered like a global event, because if you had like, let's say 5 different workers, 5 different instances listening to the same queue, each worker is going to have their own set of events. So when worker 1 starts processing a job, only worker 1 is going to see that log. But what if we wanted to see some global logs? Here is where the queue event listeners come into play. So we can now listen to queue events, not just worker events, okay, which is gonna show us whenever, or tell us whenever a job has been added to the queue, a job from the queue is now going to be processed, and so on. So that's why it's usually considered kind of a global event listener. But technically we're listening to the queue events. To create one, it's pretty simple. You have to create a class. I called it video queues event listener, which extends queue events host from NestJS BullMQ. And we have to decorate it with queue events listener. And then we would need to specify the queue name, the queue that you are going to be listening to. So those events are going to be from the video queue. Just like we have this onWorker event decorator here, we can also use onQueue event here. And here we have a list of events that you can listen to that are related to the queue, to the video queue in this case. So I like to listen to added. Anytime a job has been added to the queue, we are going to log this. Here I'm just using a logger instance just so we can differentiate between the console log here and this logging from the queue itself. Of course, we would need to also register it as a provider in app module. I already did that. And now let's go ahead and test this out. But first, I made sure that I can only run 2 jobs concurrently inside of this specific processor or worker or consumer. So 2 can be processed at a time, meaning 2 can be active at a time by this worker specifically. But we are still going to see all the jobs that are being added even though they are in a waiting state. So let's check that out. I'm going to open Postman here, going to send many different requests. And if you take a look, we can see that all those jobs were added, okay? But only 2 jobs are being processed at a time. And that's again because concurrency is 2. The point of this small example now is just to show you that we can also have queue events, which are kind of global. If you remember earlier on, whenever we were adding a job to the video queue, we were setting this job type or job name, which we set as process. What if our video queue had different type of jobs that can be processed in different ways? So a video might be processed, a video might be compressed, maybe we need to do something else with a video. So we have different type of jobs on this video queue. To be able to differentiate them, of course, we can send different names, which is the job type or job name. So let's say we had this compress job, for example. So inside of the video controller, I added this compress route handler, which is also going to add a job to this video queue. We could have the same payload, it could be a different shape, we could be using a different contract or interface or type or whatever. But the main point is that we have a new job name. How can we actually handle that? Well, in video worker, this process method is actually going to process all the different job types or job names as long as they are from this video queue, of course. So what we could do here is we could add a switch case and then check the job.name, and then based on that name, we could either compress a video, call the compress method, or do whatever needs to be done, or call, for example, the process method. Now, if you used to use Bull, which is an older package than BullMQ, but created by the same team, previously we could create different processing methods. So we would use @process, and then here we would specify the name of the job. So for example, we would say compress, okay? And this compress would actually handle the compress type from this video queue, but this does not exist anymore in BullMQ. Instead, the way they recommend we follow is just simply using a switch case. So just to show you a simple example, inside of process, we would just have a switch case on the job name. If we have a job of type compress or a process, we would do different things. Now here I'm just simulating this progress of waiting 3 seconds before increasing the progress that we saw, but we're gonna get starting compress task, and then for process we're gonna get start processing task. Let's try to actually call this compress method now. So first let's call process. If you call it, if you take a look at the logs, we can see processing a new task, starting a process task. So this is the log from the switch case here. But if we were to call compress, for example, if we hit send, starting compress task, it's gonna do something different because the job name is different, it's compress here. Now this section is dedicated to scaling. So far we've seen how to implement a worker, one single worker, even though it has a higher number of concurrency than one, so it can run tasks in parallel, but it's one worker and it's running on the same service as the main application. So there is some shared resources here. And this is absolutely fine for small applications, just like this one, for example, or in applications where you don't have a lot of users. It is absolutely fine. And I've done this before and it worked perfectly. You can configure the concurrency, put some rate limiting, just like we've seen, and so on. But if you want to scale, and if you have a lot of users, a lot of CPU intensive tasks that need to be run, and this isn't enough for you, what you would need to do is move that worker out of this service and put it in a separate service or in different microservices as dedicated consumers or dedicated workers. And this is pretty easy to do. And it is pretty beneficial if you are scaling, because if they are dedicated different services, you can easily scale them either by improving the resources, adding more CPU power, more memory, whatever you need, or you can also scale them horizontally by adding more pods, more instances. Of course, here Docker and Kubernetes come into play, and you would need a proper infrastructure. Now, to show you a quick example locally, what I'm going to do is I'm going to create a second NestJS application, okay, which will have one dedicated worker, which is not going to have anything else other than this video processor class and this queue event. And then I'm going to keep the worker here. So we're going to have one worker, which is this one right now, in this specific or in this main application. And then we're going to have a second worker in a separate application, which is just a dedicated worker. It doesn't do anything except consuming jobs from the queue. So we're going to end up with two different workers. So as you can see, we now have two different instances. One is the main application, which has this controller right here. And the second application is not going to have this video controller. So I'm going to remove it. It's just going to have this video queue right here and this worker, which is going to be dedicated for it. And then, of course, let's make the proper changes here. Let's remove the controller, move the controller from the second one. And of course, in main.ts, it shouldn't run on the same port. I'll just set this to 0 just to make it run now. And let's see what happens now. So I'm going to start both services. And now what we basically have is two different applications running. One doesn't have any APIs, anything. It just connects to the same. Be careful, you need to connect to the same Redis instance, which is the locally ran instance that I have using Docker here. And of course, we have the same queue that you are listening to. So here I created a video processor as well, listening to the same queue, doing the same job. But this time it's a separate application that can be hosted somewhere else on another machine with its own resources, which can be scaled. So we are running both. We have this queue listener. Now let's see what happens whenever we send a job. I press send. As you can see, this job was processed by the worker on the left. If I hit send again, this time, as you can see, job 65 is being processed by the worker on the right. If I hit send yet again, left side. send again, right side. So as you can see, each time I press send, if you take a look at the logs down there, you can see that it's being divided in a round robin fashion. So each time, in order, Redis is going to give that job to one of the available workers. And of course, here we have a concurrency of, if we take a look again, our concurrency is 2. So each worker can maximum have 2 jobs running at the same time. So since we have 2 workers, 2 times 2, that's 4 jobs running at the same time, 2 in each separate service. So now we can scale this application to the left by creating different instances of it, by adding some CPU power, some memory power, and we can also, if we don't want to actually have a worker here on the main app, we can go ahead and delete this video worker here. That way, this main service only plays the role of a producer. So it just produces and throws jobs to that Redis queue, and then the second service will just take those and run them in the background as a separate service that can be scaled separately. And this is how you can easily scale and protect your main app from overwhelming resources, from latency, from delays, and your users will be happy with you. Also, I don't know if you guys noticed, but if you take a look, if you remember, I said that the queue listener or the queue events are global. So technically, if you take a look here to the left side, job 80 has been added to the queue and job 81 has been added to the queue. We got the same logs from the queue in the second worker. Job 80 has been added to the queue. Job 81 has also been added to the queue. But here, job 74 has been completed and we are processing a new job which is 81. However, on the left side, we have completed 73 instead of 74 and we are processing 80 instead of 81. So now you can understand why the queue events are kind of considered like global events, because you can see them from any worker, okay? But of course, the worker events are specific to the currently running service or currently running worker, which is why on the left side we only saw that job 73 was completed, and on the right side we saw that job 74 was completed. If you want to see the completed jobs globally, what we could do is, inside of the queue event here, we could go ahead and add active, for example, or completed, and so on. That would make them global to all of our workers. This is just a side note to help you with more details. Also, one more thing, let's say in worker to the left, I'm gonna call them worker A and worker B. So worker A is to the left, worker B is to the right. Let's say worker A has a concurrency of 5 and worker B has a concurrency of 1, meaning B, the right side, can only run one job at a time, okay? And the first worker, which is A, has a concurrency of 5, meaning this worker can run 5 jobs at the same time. And this could be in a real life scenario, because let's say worker B, which is hosted on the same main application or your main backend, you don't really want to do a lot of jobs at the same time. So concurrency of 1 is enough, maybe in this case, depending of course on the job size, of how CPU intensive that job is, and so on. And we're going to assume that A, okay, worker A doesn't really do much other than processing the video, which can be actually a lot of tasks, but it's not the main app, so it's fine, and you can scale it. So concurrency of 5 is fine here, okay? So let's see now what happens, because before, when we had concurrency 2 and concurrency 2, it was being distributed in a round robin fashion, one here, one here, one here, one here. Now let's see if the first one can actually take 5 jobs in parallel and the second one can take 1 job in parallel. What would happen in that case? I'm gonna go ahead, empty everything here and run everything from scratch. And to the right side, to my right monitor, I have my Postman opened, send a job. First one is being handled by B. Send again, A. Send again, as you can see, it's being handled by A again. If we hit again, now it's also being handled by A. If we hit again, now it's being handled by B. I'm gonna spam it a bit. As you can see, A is the one getting the new jobs because A has a higher concurrency than B. So as long as one of the workers is able to take a job and the others are not able to take a job, Redis will give that worker the job again, even though last time it gave it to it, because it is available, simply. But as soon as both are available, it's gonna respect the round robin fashion and go back to the ordering. I hope this makes sense to you. I try to make it as easy as possible. If this video was helpful, please make sure to leave a like, comment, share it with your friends, and I will see you next time. Thank you for watching.